Hello YouTube, my name is Tim Rolfe. I run a tiny advanced materials research lab in Washington, D.C. called Synthetic Metals. We specialize in making high performance Fe2O3. When I say high performance, I mean ultra high surface area Fe2O3. Been doing it since 2008. It is all we do. In this video, I'm going to demonstrate performance tuning of nanothermite using performance tuned iron oxide. To the best of my knowledge, we are the first entity in the world to figure out how to performance tune iron oxide at a commercial scale, which means we're not doing it in single grams, we're doing it in kilograms of tonnage. What is performance tuning, you ask? Performance tuning refers to starting with a single synthesis or manufacturing process, and by modifying the variables, heat, temperature, gas mixture, etc., you're able to modify the resulting grain size and surface areas. I want to touch for just a second on the scientific debate, nanoscale versus nanoporous. The traditional PhD method for maximizing surface area is to make the grain size as small as possible, and that definitely works. But there's another method that's largely ignored, and that is the nanoporous route. And with the nanoporous route, the particles are not small and spherical. They're much larger. They're micron size, which means by a factor of 1,000, but they're porous. And that porosity gives them ultra high surface area. We are seeing surface areas significantly higher than what PhDs are getting with their nanoscale particles when you're outputting at a commercial scale. Special thanks to Ordnance Lab for their videos, for giving us a template. This is our first rodeo. So without further ado, let's boogie. Let's begin by defining our testing protocol. There are many varieties of thermite. We will be dealing with the aluminum Fe2O3 variety. You see the quantity there. We've got 3 grams of aluminum plus 9 grams of Fe2O3. For all 7 tests, the same aluminum is being used. It was sourced from Sky Spring Nano, easy for me to say. Average grain size you've got at 18 nanometers, a surface area at 15 meters squared per gram. For reference purposes, a U.S. football field is 75 meters squared per gram, so a gram of aluminum can cover about 2/3 of a football field. This material was bathed in a desiccant for 7 days, and I will generally characterize the mixing method as mechanical and low shear. A word of warning when mixing nanothermite: don't use a Breaking Bad Walter White mixing method. This material is not stable. Got it? Get it? Good. This is what the 7 samples of iron oxide looked like before being mixed with the aluminum. First up is Fe2O3, purchased from Amazon. Amazon recommended. Particle properties and burn characteristics are listed in the column below. Note that all 7 burns were videoed at the slow motion setting of my Galaxy S21, and that is 240 frames per second. Here we go. And this is what the afterburn looked like. Next up, the only nanoscale Fe2O3 being tested here, nanoscale Fe2O3 sourced from Sky Spring Nano. Again, particle and burn characteristic analog data displays below. The Fe2O3 SkySpring nanoscale burn was characterized by a very fast ignition, but it also burned out very quickly. This is what the afterburn looks like. The next two burn results surprised me. Both were made from our industrial grade precursor, 80% of the quality for 20% of the laboratory grade precursor cost. This sample failed our in-house phosphate aqueous absorption performance test, but it performed like a rock star in this nanothermite demo. Here we go. This is what the afterburn looked like. While sample 4 passed our in-house phosphate performance test, albeit slowly, it was a complete dud in this nanothermite demo. Take a look. This is what the afterburn looked like. Notice the unburned thermite lining both the inner lip of the pot and the top of the residue pile, which is easy to identify given its mustard-like color. This is where things get interesting, testing Fe2O3 when the surface area breaks into the 3-digit range. Given its large grain size, ignition sputters for about the first 30 seconds, but once fully ignited, the burn duration is a whopping 8 times longer than that of nanoparticles. This is what the sample 5 afterburn looks like. Note the unburned thermite both inside the pot and splattered across the tray, from which we can draw two conclusions. First, on the negative side of the ledger, this clearly was not an efficient burn. But second, on the positive side of the ledger, even with a burn duration 8 times longer than that of nanoparticles, there was still gas in the gas tank, which could further extend the burn duration if the burn efficiency could be improved. In this demo and the next, the precursor material gets a significant upgrade from industrial grade to laboratory grade. If you can stomach the precursor price going up by a factor of 5, the surface area more than doubles, but the grain size also more than triples. Lots of variables in play. Let's see what happens. As with sample 5, sample 6 also displays unburned nanothermite powder in both the pot and tray. Difference is, sample 6 displays a lot more unburned nanothermite powder, meaning there's a lot more fuel still left in the gas tank once the burn efficiency can be improved. Lastly, sample 7. Same grain size as sample 6, but with a larger surface area. Let's take a look.
Sample 7 takes first prize in 3 categories. First, greatest volume of unburned nanothermite post-reaction. Second, longest burn duration. And third, what I found interesting, the continually loudest of all 7 tests.
In summary, 3 points. Point number 1, based on the 7 tests performed, I see 3 routes to improving micron powder ignition speed. The optimal result will likely be a hybrid of all 3, but since this video is over 20 minutes long, we're not going to get into that here. Point number 2, this video should be a call to action for 2 groups of people. If you are a researcher or a manufacturer whose research and or product includes Fe2O3, especially battery industry people, for example, you want to supercharge your superconductor, test drive our Fe2O3 in your products. More information on that and a limited quantity of samples can be found at. And lastly, if you like this video, please hit the like and subscribe button. Peace out.